Okay, so the last thing we saw was the classification of stresses according to the relative magnitude of horizontal and vertical stresses, and we call that stress regimes. And if you remember, we had three types: normal faulting, strike slip, and reverse faulting. And then we further said that according to the stress regime, hydraulic fractures will propagate differently. In normal faulting and strike slip, the minimum horizontal stress is horizontal, and therefore you have a hydraulic fracture which is vertical, while in reverse faulting, the hydraulic fracture will be horizontal. So today we're going to continue working with the stress tensor, and we'll see different ways of plotting the stress tensor. The stress tensor, for example, is we also saw that it's a mathematical entity, which is a little bit more difficult to write than just a number or a vector. And in this case, it's going to be a matrix. It's going to be, in our case, a matrix which is 3 by 3 because we are working in 3 dimensions, right? What is this? I was thinking about 4 dimensions. 4. Okay. You see that it takes quite a bit to write this stress tensor. And imagine, how difficult it's going to be now if we wanted to plot something like that. Many times we need to plot things to see how they vary with space, how they vary with time, because that informs a lot about processes and how, for example, the stresses change with time. So we're going to see now ways of plotting the stress tensor or simplifying the stress tensor so that we can plot it, even in 2 dimensions. All right, so let's think, before we get there, to a 2-dimensional space. And in that 2-dimensional space, we're going to plot different things. For example, I could plot a scalar like a pressure. How would you plot in 2D a scalar quantity, for example, pressure? Let's say that here there is a wellbore, and we are pumping from that wellbore, and we want to look at how pressure varies with space. Sorry? A point, but I mean, I could say, for example, here this is a point and this is 10, right? But if I want to plot this in space, usually we use, in this case, maybe a contour plot. And in this way, I can plot a scalar quantity as a function of space, right? So for example, here I could say the pressure here is, let's say, 5, and here 10, here 20, 30, and so on. So that would be a plot of a scalar field of pressure as a function of x and y, where x is distance and y is distance too. Working out?
Okay. If you're gonna do that, I can try putting the screen down and see if
you can try and make it work.
Even though you're doing it.
Yeah, it's okay. But also, this thing was not explaining well. This was pixelated.
Oh yeah.
No, but just leave the screen.
Oh, okay.
You don't need the screen to project.
So it might be a problem with the relay, which means that this would have to be down in order for the projector to turn on.
Okay, but I had the screen down before and it didn't work.
Okay, so I'm just trying to troubleshoot.
Okay.
So I don't have to do that.
Okay, I'll work here.
Okay.
Okay.
Sweet. Yeah.
So this would be a scalar field, and similarly to that, you guys see over here, I could have the same thing, and I could plot again pressure. Those lines would be contour lines of pressure. How would you expect to plot here a vector? For example, a velocity vector. Yeah, this is the pressure contour lines. And now we want to plot, this is x and y.
You can go back to here.
We want to plot a vector.
What are those?
A vector of velocity. So flow rate. Here we have a wellbore. Pressure is lowest here and increase in that direction. What is going to be the direction of the flow rate or velocity vector? Darcy velocity. Perpendicular to the pressure field. And if I wanted to plot a vector, it would be like this, right? In this case, the velocity vector is going to be the result, is going to be the gradient of the scalar field. And I can also draw it in 2D like arrows. So this is going to be now, the quantity before was a scalar field. This is going to be a vector field. What I wanted to show with this example is that we can plot both the scalar quantity and the vector field in 2 dimensions, and also you can extend this to 3 dimensions, but it will be a lot harder to do over here, but you could do that. My question now is, how are we going to plot this tensor? And probably you'll see that it gets a lot more complicated. So in order to deal with this quantity, we're going to do a few things. First, we'll talk about the Mohr circle that is going to help us to plot the stress tensor on paper or on a 2-dimensional surface. Do you guys remember the Mohr circle? Probably you remember the 2D Mohr circle, but I don't know if you guys are familiar with the 3D Mohr circle. So we're going to jump straight to the 3D Mohr circle.
Okay, so
yeah, but now you have to make the video too small. It's not fine the entire screen.
So we can't necessarily dilate it unless we actually have access to the projector. I could stand on the desk and do it right now if you'd like. You can also, if you need, you can do it manually here.
No, but I wanted to reply the entire screen.
So let's try to put the screen down. It should fill the entire screen.
It happened the same to me before. I wanted to occupy the entire screen. Don't you have the remote for this?
I can run back and grab it if
Okay.
you'd like.
Yeah, please.
Okay. So you want the image to fill the whole screen?
Yeah.
All right.
I guess something related to resolution, right?
Yeah, I can check that out.
All right. So it's going to go back. I hope this is going to continue working. Let's switch here. Okay, so we're going to talk about the 3D Mohr circle. And the 3D Mohr circle is basically one way of plotting state of stress and a stress tensor. If you remember what we did last class, we said that any stress tensor can be written as a tensor of principal stresses. And that means that I can convert this tensor into a tensor where I have just sigma 1, sigma 2, and sigma 3. And the objective of the Mohr circle is going to be to plot a stress tensor that summarizes graphically what we have in these numbers. And this works by plotting on the x-axis the normal stress. Usually it's effective normal stress, but let's not worry about that right now. And in the y-axis, the shear stress. Okay, the first step is to plot here in the x-axis the value of the principal stress. Do you remember what was the shear stress when we have a normal stress?
Okay, so to dilate the image, we're going to have to redo the program, and I mean, we could do it in class, but it would take, we don't know how long it would take, predict 30, 40 minutes and stuff.
Okay.
But we'll do it after the class, and
okay.
we just have to update the system.
All right.
Yeah, can everybody see it though? Like, is this a problem?
It's much better when
It's what?
the full screen.
Coming in?
It's much better when you have it on the full
Yeah,
screen.
no, yeah, I understand that. We just can't.
Okay, just please do it
right now.
after the class.
Okay, all right, we will. Thank you for calling.
Okay, so
Nicholas, one more
Yes.
thing. Autofocus is going in and out.
it's going out of focus.
There you go. Okay.
All right. Okay. So, all right. In order to draw this Mohr circle, what we have to do is we have to start by finding what is the value of the normal principal stresses on the x-axis. So if you remember, the definition of a principal stress was that there is no shear on that face. Therefore, if it's no shear, the shear here is going to be 0, and these sigma 1, sigma 2, and sigma 3 are going to be located on the x-axis. And I'm just going to make up some values, but remember that sigma 1 is always larger than sigma 2 and larger than sigma 3. And these are going to be the three principal stresses on the x-axis. Then we're going to draw a circle that goes from each of these principal stresses to the other, and here you have two of those circles, and there's going to be one more that is going to go from sigma 3 to sigma 1. And it's going to be that circle. We're going to see a little bit later what, how we interpret this in reality, and what each of these circles are, and how to locate stresses based on where you are with respect to sigma 1, sigma 2, and sigma 3. But for now, let's just keep it simple. And the Mohr circle is going to tell you all the possible state of stresses, and it's going to be the area in between the three circles. So inside these three circles, you have combinations of normal stress and shear stress at any orientation in a particular place where we have, let's say, sigma 1, sigma 2, sigma 2, and sigma 3. Each of these are going to be the results of shear and normal stress for a particular angle, different than the one of the principal directions. At any orientation other than the orientation of the principal stresses, we're going to have some shear. And the Mohr circle is going to allow us to compute that. So, in the next project that I'm going to tell you later on when the deadline is, but don't worry, I'll give you plenty of time. You're going to have to use the equations of the 3D Mohr circle in order to calculate those shear and normal stress. And we're going to see that that's an excellent application for calculating shear and normal stresses on fractures. For example, in the assignment that I just gave you, we have a given fracture that was detected in a wellbore, for which we know what is the strike of the fracture, what is the dip of the fracture, and if we put that into a particular place for which we know what the